Example 3, Fluid Mechanics, Chapter 7. Hydrofoil of 1.2 feet long and 6 feet wide is placed in a seawater flow of 40 feet in a second with the density of 199 slug on foot cube with the kinematic viscosity of this quantity. Estimate A. The boundary layer thickness at the end of the plate. B. Turbulent smooth wall flow from the leading edge. From the leading edge. C. Laminar turbulent flow with Reynolds transition. Turbulent roof wall flow with epsilon equals C and D. Delta at the end of the plate. For the calculating delta, we should first calculate Reynolds L, which is equal to UL on nu. We have the velocity is for T. Kinematic viscosity, which is equal to so we now calculate delta at L on L, which was 5, or for the hydrofoil and turbulent flow we have the relation for this is greater than transition Reynolds, as this is turbulent. So now we can calculate the thickness at the end of the edge, which is equals to the multiply to B. For fully turbulent smooth flow, the drag coefficient V drag CD equals to this relation Reynolds L 1/7. and C. So we can now calculate the drag force. The drag force is CD multiplied to the let me write U square A. We have density, velocity, and AL multiplied to B. The drag force can be calculated and is 80 pound force. And the C section, with the laminar flow, we is calculate drag depends on the transition Reynolds. In this case, we have a conditional relation for before, which had two drag force for the hydrofoil based on our transition Reynolds. And the Reynolds transition is equal to this relation. In this case, we have the transition of case number 1. So we are going our continue our calculation with this formulation. So we can calculate drag on the Reynolds L, which calculated before. In this case, the Reynolds number can be calculated. The drag is calculated is so we have drag equals to CD multiplied to 22.4 and D depending on the epsilon equals to 304. We have a relation based on the availability of our information. The drag force based on the epsilon as noun can be write as this equation. From the relation in the book, we have a relation for drag based on the roughness of the plate for an immersed body, not for a duct. So we can calculate the drag force coefficient L, which is 9.2. The drag coefficient can be calculated and is this quantity. At the end, you can calculate drag from U to A. In this case, drag is 0.4.